Mark Zoback is the Benjamin M. Page Professor of Geophysics. He's the former director of the Stanford Natural Gas Initiative, former co-director of the Stanford Center for Induced and Triggered Seismicity, and a former co-director of the Stanford Center for Carbon Storage. Dr. Zoback conducts research on in situ stress, fault mechanics, and reservoir geomechanics. He's the author or co-author of over 300 technical papers. He's got 5 patents in his name and the author of 2 books. Mark retired from Stanford in April of 2021, but he did so with an agreement to host an SCCS webinar every year. Oh yeah, that's the first he's heard of this.
Yes, it is.
Today's webinar is titled Meeting the Challenges of Large-Scale Carbon Storage and Hydrogen Production. Today's presentation is based on a recently published paper with the same title that was jointly authored by Mark and Dirk Schmidt of Shell, and it appeared in the November 2022 edition of the Proceedings of the National Academy of Science. And it's also available on the SCCS website. So without any further ado, I would like to hand it over to Mark.
Okay, thanks for joining us today. And the title of my presentation is a topic I've been talking about for several years. The interest in large-scale carbon storage has been of great interest and increasing interest for the reasons you all know about as a critical mechanism for reducing greenhouse gas accumulation. The paper that Sarah mentioned, which is sort of the point of departure for this talk, was published actually just in March. And Dirk and I wanted to provide a perspective on a strategy focusing on large-scale carbon storage and hydrogen production. And the reason we wrote this paper is it's not hard to look at the pace at which things are occurring and have some concern. I've used this slide for a number of years. It shows something that was originally done by the IEA and picked up by OGCI and others. This was first published in 2017, showing the expectation of the rate at which we have to be storing CO2 in the subsurface as a function of time. So it's not a cumulative plot, it's the annual rate at which we have to be storing CO2 in the subsurface. Actually, in recent years, it's actually, gotten a little bit more aggressive than this, but to be at roughly a gigaton of CO2 per year by the end of this decade, to be at 3.5 gigatons by 2035 to 2040. To put that number in perspective, that's a volume equivalent to the total global oil production system. All of the wells, all of the pipelines, all of the facilities. It's a gigaton of this, a gigaton of that. It's a little hard to get your head around the numbers, but you have some sense of what global oil production, distribution, and utilization involves. And so it's a mind-boggling number. And by mid-century or so, we've got to be at twice that. So it's a huge endeavor. And sadly, we're not even off the horizontal axis yet where we are now. So what we have to do in the short and intermediate term is, it's at a scale that's it's really hard to get your head around. I'm not going to be talking about hydrogen very much, except it was one of the motivations for the paper. And this is one anticipation of how hydrogen and ammonia use are going to grow through mid-century. And it's actually even more profound than this, because there's a lot of interest now in Japan and Korea of using ammonia in their coal burning power plants to lower the greenhouse gas, the greenhouse footprint. Some of you may know that when following Fukushima, when Japan shut down 50 nuclear plants, they rapidly went to coal, and not a step in the right direction if you're interested in greenhouse gas accumulation. One way of reducing the impact of that coal is to use ammonia, which will burn directly. And so the ammonia market may go up very dramatically just for that one single use. The figure on the right was prepared by DOE. Naomi Bones added the superhero, which I think is a great improvement. Dirk and I are talking about sort of what's traditionally called a blue hydrogen strategy that is making natural gas, making hydrogen from natural gas and sequestering the CO2. And then you can take that hydrogen and use it for a wide variety of sources. And I just mentioned ammonia as a fuel being one of those. If you look at this carefully, a lot of independent people who've looked at it have argued that these blue pathways, as they're typically called, can be pretty green. In other words, you can get the total carbon footprint very, very low. For example, using autothermal reforming instead of steam methane reforming makes the carbon capture part very, very easy. And if you can sequester that carbon, if you be using sort of certified natural gas where the pipeline system is free of leakage, blue can be the new green. Now, there's a tremendous bias, I think, in the hydrogen world toward green hydrogen, making hydrogen via electrolysis, sourcing the electrolysis with renewable sources of electricity. What Dirk and I show in the paper is if you really want to go all in on hydrogen and electrolysis and use renewable sources, the land use requirements are really quite appreciable. On-land solar is shown in yellow, offshore wind is shown in this sort of magenta color. So what's wrong with green hydrogen? Absolutely nothing, but it's expensive. It's much more expensive than blue hydrogen today. And electricity keeps getting more expensive. Wind and solar are getting cheaper, but electricity is getting more expensive. And you've got these large land use issues, public acceptance. It's going to take time to be massively constructing electrolyzers. So these things can happen in parallel. The very first sentence of the conclusions of our paper is that in the era of decarbonization, no idea is a bad idea, right? Anything we do, everything we do to lower carbon emissions is a step in the right direction. But Dirk and I wanted to talk about scale. We wanted to talk about safety and public acceptance. We wanted to talk about something that was economically viable, not always dependent on government subsidies. The subsidies are great, but they're not going to last forever, and they're not globally available. And focusing also on what can be achieved in the next decade. A good example is small modular nuclear reactors. I think any hard look at the future of decarbonized energy includes small modular nuclear reactors, but they're really not going to be a viable option, for 10 or 20 or possibly more years. So, this is a perspective on getting started and getting started soon and getting started at scale in a way that makes sense. So as all of you know, there are many options, but two principal options for storing CO2 in the subsurface: saline aquifers, porous, permeable sedimentary formations full of saline brine, has no economic value, and they are widely distributed. The other is, of course, depleted oil and gas reservoirs, similar geologically, except the oil and gas has been produced and they have been depleted and therefore represent an opportunity for injection of CO2. So I want to focus on these two, and I want to start with the saline aquifers because it's gotten the most attention. And if you look at the DOE CO2 storage atlas, the numbers of available pore space are just truly enormous. They're more than adequate for anything we can conceive of doing. But assessments of pore space and its suitability for CO2 storage is sort of just the beginning. I mean, many of these are not going to work for all sorts of reasons other than their geologic suitability, although some of the reasons they may not work, have to do with the hydrologic properties. Are they permeable enough? Can we, inject enough without changing the pore pressure too much in any kind of feasible way? And every one of these is going to require extensive characterization. Now that's a straightforward process, but it takes time and it takes money. And just as an aside, I've been asked, as a consultant to advise a company who's interested in storing CO2 in the subsurface. And the dilemma the company faces is they have a site in mind, but they're going to have to spend several years collecting seismic data, drilling wells, analyzing the data, making models, assessing the models, and if everything goes well, applying for a permit. But if everything doesn't go well, if that site turns out not to be suitable for the volumes of CO2 they're interested in injecting, it's going to cost $10 or $20 million. It's going to take 3 to 5 years. And at the end, they may not have a site that's suitable. So, this is a difficult process when put into practice. The regulatory requirements are fairly rigorous. They should be rigorous. That's not a complaint, but they're also evolutionary. We've not done this at scale, and that's going to be a challenge. And there's an appreciable risk of induced seismicity, which is really what I want to take some time to talk about. This slide was put together by my colleague Bill Ellsworth to talk about the earthquakes that were of increasing occurrence in the central and eastern United States. As you can see, this goes back to 1970 when magnitude 3 earthquakes were, being detected and located anywhere, in the United States. And, around 2005, there was a significant deviation from that, and it really took off around 2008. And, something is happening. Now, this was coincident with the explosion of unconventional oil and gas development in the U.S., horizontal drilling and multi-stage fracking, which was very controversial at about this same time period. And in many people's mind, the great majority of the seismicity was associated with fracking, as it was referred to. And the answer is it's actually not. Some is related to hydraulic fracturing, but most is actually due to the injection of water that was being co-produced, with the oil and gas, very saline water that was being injected into saline aquifers, resulting from the horizontal drilling and multi-stage fracking. And so that's, in a sense, the main issue. So, a relevant experiment of large-scale saltwater disposal and earthquake triggering, when we consider what's going to happen when we inject large volumes of supercritical CO2 in the subsurface. So we started working in Oklahoma a decade ago because of the increase in seismicity. The plot on the right is from one of our papers and showing the pressure change at the depth of the earthquakes, which is at about 6 kilometers. That's in red. It doesn't get very large. That's 0.2 of a megapascal. So that's about 30 PSI. And the earthquakes are shown by the circles and the larger earthquakes by the yellow stars. And you can see, this is an enormous area, 300 kilometers by 250 kilometers. And so a lot of earthquakes were occurring. When the situation was most critical, there was a magnitude 4 earthquake every week being felt by basically everyone who lived in northern Oklahoma and southern Kansas. Now, the origin of this produced water disposal is the fact that oil prices were high, and there are formations like the Mississippi Lime. These black layers are representing the producing zones. These were, well-known oil-producing formations, but were characterized also by very large amounts of water production. So because oil prices were high, some enterprising companies drilled large diameter wells down into the Arbuckle Formation so that they could separate the oil and water at the surface, direct the water to these injection wells, and inject the water down into the Arbuckle. Now, the Arbuckle would seem to be absolutely ideal. It's very thick, it's porous, it's permeable, about a Darcy, it's laterally extensive, it's throughout this region, and it is even subhydrostatic. The Arbuckle outcrops to the east at an elevation about 600 feet lower than the elevation here in north central Oklahoma. So the water literally just falls into the well. No, you have to pump the water to the well, but the surface pressure is essentially zero, other than the the friction in the pipe. So it's ideal. The Arbuckle had been used for a disposal over the years, small amounts of disposal, but now, excuse me, and now the volumes are significantly increased. About 200 million cubic meters were injected in 2015 alone. What we soon realized, once we figured out what was happening here, that the earthquakes were occurring, down in the basement, okay, not in the Arbuckle, because the Arbuckle, is in direct contact with the basement. And critically stressed faults in the basement are hydraulically conductive. This is some research we did many years ago, which I'm not going to take time to discuss, but the pressure changes in the Arbuckle were transmitted down into the basement and, into these critically stressed faults. And I'll show you some data that shows that. But the other thing that's very important is that despite this very large volume and the many hundreds of wells that we're injecting, the pressure changes in the Arbuckle were really quite small. They probably never exceeded about 1 megapascal or 145 psi. So a relatively small change in the Arbuckle, because those pressures were transmitted to the basement, were triggering earthquakes in the basement, that were quite significant in many cases. Now, this is a different representation of that process. We're sort of showing the flux of water, how much water is being injected in any unit area in this particular plot. And I'm going to come back to that later. But there are three key points I want to make right now. First, it's not the magnitude of the pressure change. It's the area affected. In other words, there are lots of critically stressed faults in the basement. The basement's about 1.2 billion years old here. And, it's been through many episodes of tectonic deformation. And if you affect a small area, whatever you might trigger is likely to be a small earthquake, because you're gonna, the probability is you'll be interacting with relatively small faults. But as you affect a larger and larger area with this pressure perturbation, the probability of encountering larger faults, increases as that area increases. And so that's a very important concept that's going to come back. It's not the pressure change, bigger pressure changes, bigger earthquakes. It's not that at all. It's really the area that is being perturbed by the injection process. The other critical issue is that pressure change is in contact with crystalline basement. We always think about seals above the injection zone because the supercritical CO2 has about 60% the density of water, so it's buoyant and will tend to rise. That's important. But you also need seals below so that that pressure is not transmitted down into the basement, and that these critically stressed basement faults are hydraulically conductive. So that part is pretty straightforward. All the great majority of the faults in the basement are impermeable. They've been sealed up through precipitation or whatever over geologic time. But the ones that are active, producing the occasional earthquake every 10,000, 100,000 years, whatever, maintain permeability and can transmit these pressures from the Arbuckle to greater depth. Now, thanks to some really innovative methodologies associated with AI and machine learning, Young-Soo Park, working with Greg Baroza and Bill Ellsworth, have produced the map on the left. These are the earthquake producing faults down in the basement. So these faults are unknown. They're not they're not mapped in the sedimentary section, by seismic reflection data or other methods, but it's really clear to how these machine learning techniques have brought out, the details of the faults that are producing the earthquakes. Here's work by Martin Schoenball and Bill Ellsworth that, once the network was well established, once the velocity models were well determined, it's absolutely clear that the earthquakes are, at a depth of about 6 kilometers below the surface, or 4.5 kilometers below the injection zone. And the orientation of these planes are exactly what one would expect. We have very good information on the orientation and relative magnitudes of stress in this area. And in fact, you see these conjugate vertical strike slip faults. This is exactly what one would expect. We know what the stress orientation is. We know what strike slip faulting from the focal plane mechanisms, and the faults are just the critical orientation to be easily activated. And they were just there. And this process of changing the fluid pressure, even a little bit over this large area, activated all of these faults. Now, this is not totally surprising. We made this observation a number of years ago in a paper that Steve Gorelick and I wrote. And we pointed to the critically stressed crust. And these maps demonstrate that earthquakes in intraplate areas occur almost everywhere. Obviously, Western China is more seismically active than Eastern China, but these red dots represent places where dams have been built, reservoirs have been impounded, and the relatively small pressure change associated with the column of water have triggered earthquakes, big and sizable earthquakes in some cases, down in crystalline basement. So even though Eastern China is relatively less seismic than Western China and the Tibetan Plateau, there are sizable earthquakes triggered by small pressure changes. That even occurred in the Indian Shield. There's a couple examples here in the Canadian Shield where small pressure changes are triggering earthquakes. So this critically stressed crust concept is not new. We didn't discover it in Oklahoma. It's something that we've been looking at for many years. And again, as an aside, what we're able to show is that there really is no difference in the state of stress at depth in crystalline basement in these relatively seismic and relatively aseismic areas. What's different is the rate at which these areas are deforming. So the earthquake rate is not reflecting the stress level. It's actually reflecting the strain rate, the rate at which the brittle crust has to deform, sort of to keep up with the rest of the lithosphere, which is a function of, heat flow and, lithospheric structure and plate driving forces and all the rest. But the stress is high everywhere, and small perturbations can trigger seismicity. So what we're really talking about, we can use the words induced seismicity and triggered seismicity as if they're synonymous, but they're really not. What we're really talking about is a triggering process. We're talking about geologic forces that build up, stress, like a spring pulling a block, and when the block slides, that would be equivalent to an earthquake, and the stress on the fault dropping, and then the process builds up. Living on the top of the San Andreas Fault, we recognize that this process is repeating every few hundred years. In an intraplate area, it could be every 10,000 or every 100,000 years. But what the fluid injection does is it raises the fluid pressure, it lowers the effective normal stress, and simply allows an earthquake that would have occurred at some time in the future to occur now and release the accumulated energy. So the energy is already in the earth. The fluid pressure change is simply triggering the release of that energy by perturbing the normal stress or reducing the effective resistance to sliding. So what Dirk and I are arguing is that if you want to store very large volumes of CO2 in the subsurface, the first thing we should look at are depleted oil and gas reservoirs. And we used Oman as an example. Shell has a long-term engagement in Oman, so we had a lot of data available to us. But when you think about the fact that 3.5 gigatons a year is equivalent to the volume of oil, volume of CO2 we might be like to store when we're sort of at the gigaton level, it really means that every depleted oil and gas reservoir in the world can potentially store large quantities of CO2. So you have a lot of optionality. And there's a lot of existing knowledge of the subsurface, both static, geologic structure and properties, and also dynamic in the sense that, the pressure goes down when you produce the oil or gas, where, you may have injected water or done some other form of secondary or tertiary recovery. So, there have been decades of study of, fluids in these formations and how they respond. So, a lot. There's a lot of infrastructure already in place. Public acceptance is much easier. These are existing industrial sites. There's essentially no risk of induced seismicity due to pressure depletion. I'm going to qualify this slightly, but the pressures are depleted, and that gives you some sort of freeboard when you start raising pressures. There's a potential positive impact on oil production when the CO2 is being used for enhanced oil recovery. Now, the downside is the infrastructure, does pose a risk. And the other reason for talking about Oman is it's an example of a place with a large portfolio of oil and gas fields, and you want to choose the places you work very carefully to try to not work in places where the infrastructure is more a threat than it is a benefit. And so not all oil fields are going to be suitable. They might be suitable geologically, but the infrastructure may actually pose more of a risk than a benefit, and you simply just don't use those. Now, there's another phenomenon associated with this wastewater or produced water disposal that I need to mention, other than injection into basal aquifers. What's happening in West Texas, and we're here in the Delaware Basin. The Delaware Basin is the westernmost part of the Permian Basin of West Texas. Mexico is here, New Mexico is up here. And here what's happening is the produced water from the unconventional development in the Delaware Basin is being injected into this Delaware Mountain group, this group of formations that are colored yellow here. Now, this is well above the basement, so the earthquakes are not occurring in the basement. They are occurring in the Delaware Mountain group and a little bit in the Bone Spring. And so it's the same phenomenology. The increase in pressure is allowing slip on these faults. But the important thing here is the slip is limited. Above the Delaware Mountain group is salt, the Ochoan salt. And then below the Bone Spring here is the Wolfcamp group, where a lot of the horizontal drilling and multi-stage fracking is occurring. And these are shaley formations. And so the earthquakes, basically stay limited to the Delaware Mountain, and therefore they're limited in size. And the magnitude of these earthquakes has been limited to about magnitude 3.2, basically because the faults are limited in extent by the salt above and the shale below. Excuse me. Up here in this Mentone area, they've been doing deep injection, and they've in fact had a very significant earthquake, magnitude 5.4. So, this phenomenon is relatively safer, lots of earthquakes. It's sparsely populated, but the earthquakes are small enough that they're not really going to cause very much damage. There are other issues associated with shallow disposal. For example, old wells are sometimes breaking out at the surface, and salt water is occurring in ranch land, and that's undesirable, of course. And so in some places, the deeper injection is going on, But where the deeper injection goes on, that's where the earthquakes are getting larger in magnitude. So it's a tough choice to have to make. Now, Noam Dvory and I demonstrated that in this Delaware Mountain group, where there had been prior oil and gas production, that's all the purple area here. This is, this is where production had occurred. Injection is occurring everywhere now, but earthquakes are only occurring where production had not occurred. In other words, where the Delaware Mountain group was a saline aquifer, the current injection is triggering earthquakes. Where the Delaware Mountain group is a depleted reservoir, you are getting earthquakes. You're not getting earthquakes, sorry, because the pressures are depleted. And in this area where the earthquakes are occurring, once again, we see the pressure changes. This is work done by the University of Texas in the scissor group. The pressure changes are again quite small, only less than 100 psi, and sometimes only a few tens of psi. So the good news is that the earthquakes, when it's geometrically restricted and not in contact with the basement, the earthquakes stay small. But the bad news is that once again, even small pressure changes cause the earthquakes. Now, what Noam and I did in our paper is we demonstrated this depletion process using a presentation of stress pore pressure data that we've been working with for a while. So this is pore pressure normalized by the vertical stress. This is the minimum horizontal stress normalized by the vertical stress. This is a normal faulting area. So the driving stress is the overburden. It doesn't change, but the minimum stress is what controls whether the faulting will occur or not. And as you deplete a reservoir, you sort of move to the left, the pore pressure goes down, and the stress goes down poroelastically. This diagonal line here represents frictional faulting or the normal faulting situation. And when you're in a critically stressed environment, and for a normal faulting domain, you'll be right along that line. And that's exactly where things started in 1974. But as production occurred in these wells up here, you move away from the normal faulting line. So production normally stabilizes faults, and that's exactly what we see happening here, which is why the production in this area where the purple wells are located, you're not getting earthquakes now because you can increase the pressure, you can move to the right, but we're pretty far from the normal faulting line. So in most cases, depleted oil and gas reservoirs should be useful, but they still require some geomechanical due diligence. And I want to talk about that for just a minute. Before I do, however, I want to make the point that the word depletion, as I'm using it, means pressure depletion. And there was a unfortunate occurrence of induced seismicity in an offshore gas field in the Mediterranean. And it was an abandoned and depleted oil reservoir, which was being considered for use as a natural gas storage site. There are 400 of these operating around the US, and they needed more gas storage sites in Spain. And so they did an experiment where they injected a little bit of fluid and they immediately got earthquakes. Well, this was the depleted reservoir. What's going on? Well, what's going on is shown here. This reservoir is a very strong aquifer support. And so here's the depletion of pressure that occurred due to production. But when production stopped, the pressure built back up just due to this aquifer support to the point where they were basically back to the initial conditions, so that a little bit of a perturbation caused the earthquakes. So, rule number one then is make sure if you're using a depleted reservoir, the pressures are still depleted. Then Sam Hashemi and I have been following up some work I did with Jeremy Brown a number of years ago on what's called stress path. So this is that same kind of plot. Here's pore pressure. It's not normalized now by vertical stress. And here's the minimum stress. There's the normal faulting line. There's the maximum stress. And this is actually a Gulf of Mexico field, a Vicksburg Formation in the McAllen Ranch. And so these are all data out of the literature. And what happened over time is that the pore pressure and the stress followed that blue line, and it became more stable, less further away from normal faulting as a function of time. Now, what accompanies that, of course, is some degree of compaction, right? You're reducing the pore pressure, and of course, what accompanies that is a permeability loss, which can be quite appreciable, and that has to all be taken into account. But what's really interesting, and the work that Jeremy Brown and I did, is that, okay, now what happens if we were to use this and start injecting and increasing pressure? Well, do you go up this line? Well, maybe the formation has changed its properties, so the slope might be slightly different. But if you inject too much and you raise the pressure too fast in limited areas, what happens is this, and you actually change the pressure faster than the poroelastic stress change occurs, and you can actually hit the failure line at pressures much less than the initial pressures. So you've got to be careful, okay? So depleted oil and gas reservoirs, have their own issues, but it's a better starting place, I think, and puts you in a better position to avoid induced seismicity. And so, to me, the problem with induced seismicity represents a binary risk, and I want to make that clear here. So I was looking online at some examples of proposed projects. Now that the IRA legislation has offered an $85 a ton tax credit for injecting CO2, into a saline aquifer. So here's one company that is proposing a 2,100-mile pipeline. It connects about 20 different corn ethanol plants. Now, one can question whether we should be subsidizing corn ethanol, but now there's a potential to subsidize the subsidized corn ethanol by making it, less of a greenhouse gas footprint. So the idea is to collect CO2 at all these different sites and put it through a 2,100-mile pipeline system at a cost of about $4.5 billion and inject 12 million tons a year in saline aquifers in North Dakota, where there is no CO2 injection going on at scale at all. Now, there are a couple of pilot projects that are being discussed, but we don't know if they're going to work. Will they scale or so on? But, here's a proposed project. That pipeline system is now shown in green. What's shown in blue is another pipeline system, 1,200 miles of pipeline that wants to inject 15 million tons of CO2 per year at Decatur, Illinois. Here's another pipeline, almost 300 miles, another 12 million tons of CO2 coming from Iowa into the Decatur area. So let's take a look at Decatur. Decatur is a place where there's been a few 100,000 tons of CO2 injected every year down into the Mount Simon sandstone. It comes from a corn ethanol plant, and nothing serious has happened. In other words, there's been a lot of seismicity, but the earthquakes have been small, typically magnitude -1 or so. The pressure change is comparable to the Arbuckle, about a megapascal or less. But what's also clear is that the earthquakes are penetrating faults down into the basement. And I would argue the concern about Decatur is scaling it up will change the pressure over a larger area, even though the pressure change, if you put enough wells in and you spread them out, the pressure change may not get very much larger, but by changing the pressure over a larger area, it's potential for larger earthquakes to happen. This is a figure from a study, it's over 10 years old, from the Lawrence Berkeley Lab Group. And I've always really liked this paper. The context of this paper when it was written is that, we're going to collect CO2 from 200 coal burning power plants along the Ohio River. We were going to pipeline it to this Illinois basin and use about 20 wells for injection. And they went through various scenarios of how much you would inject for how long. And they actually had geologic controls on the Mount Simon, and then they varied the model and went through a bunch of different scenarios. And the point that really struck me about this study is that this, even after 50 years of 5 million tons a year from each of these wells, the CO2 footprint doesn't go very far, but the pressure change goes quite far. And these are bars now, 30 bars or 3 megapascals. And that's 3 megapascals, 450 PSI over, 200 kilometers is a large pressure change, in the Mount Simon being, transmitted down into the basement. And so it's a basal aquifer, and those are the problematic sites, the most problematic sites in my view. Here's the Quest site. The Quest site is in Alberta, not far from Edmonton. It's a very analogous kind of situation. The injection, few 100,000 tons a year, is going into a basal aquifer, and they're getting earthquakes down into the basement. Again, the earthquakes have been small, although there recently have been some magnitude 3s in the general area, which I'm not sure if they are at Quest or they're near Quest, but nonetheless, it's very analogous in the sense that it's not a huge volume, but it's into a formation in immediate contact with the crystalline basement. Now, Steve Gorelick and I put this figure together in our 2012 paper, which I'll talk more about here in a minute. It's a figure based on relationships that are well established in earthquake seismology. And it basically relates the size of an earthquake here on the left in terms of magnitude, here on the right in terms of the moment, which is the area times slip times elastic modulus, as a function of the size of the patch of the fault that slips. In other words, the San Andreas fault is a huge fault, but it has 1 million magnitude 2 earthquakes for every magnitude 8 earthquake. And, a magnitude 2 earthquake means a small patch of the fault will slip, whereas a very large earthquake will, of course, involve slip on a large fault. So when we talk about these strata-bound earthquakes, such as in the Delaware Mountain Group and sort of magnitude 3-ish earthquakes, we're talking about slip on faults of a few 100 meters in size. And the amount of slip kind of depends on the stress drop, but it's a few millimeters, maybe a centimeter of slip on the fault. When you start talking about magnitude 5.4 earthquakes, such as the Mentone earthquake I talked about before, the 5.8 is the Pawnee earthquake. That's the biggest earthquake that occurred in Oklahoma. We're talking about earthquakes that can cause damage, but are certainly very widely felt. These earthquakes, require a fault of a dimension on the order of 10 kilometers to occur. So it's clearly these basement-rooted faults that are most probable, and the only faults that are likely to cause earthquakes that have the potential to do damage. And we've seen this over and over again. The larger earthquakes greater than magnitude 4 associated with fracking in the Horn River area of British Columbia were occurring because the fracking was occurring right above the basement, and it was nicely shown that the bigger earthquakes are on faults extending down into the basement. The same thing is occurring in China. They're fracking near the basement interface, and they've had earthquakes as large as, they're reported to be as large as magnitude 4.99999, because the policy is that no earthquakes magnitude 5 and larger are occurring. That aside, there have been fatalities in some of these earthquakes, and some have probably been significantly larger than reported, but it's occurring because you're stimulating slip on basement faults. This is more work from TexNet and Scissor at the University of Texas. What's been happening recently, these small earthquakes in the southern Delaware Basin have been going on for quite a while, but now, more recent times, the Mentone earthquake, which I pointed out before, and a number of sites in the Midland Basin are clearly due to deep injection. So this is showing shallow saltwater disposal in yellow. The deep saltwater disposal increased markedly around 2015, 2016, and that's when these larger earthquakes started to take off as well. So again, it's these basal aquifers, and just like in Oklahoma, the faults that are lighting up make perfect sense with respect to the regional stress field and Coulomb faulting and all the rest. So where I am today, is that these large-scale basal aquifers may not be feasible. Dallas-Fort Worth Basin, the injection into the Ellenberger there caused basement faults. What we saw in Oklahoma, basement faults. What we're seeing now in the Permian Basin, the bigger earthquakes, basement faults. And so you have these large regional, such as this basal Cambrian sandstone, which are, a lot of available pore space, but really, really potential is that they may not be feasible at all. So this paper I wrote with Steve Gorelick in 2012, we argued that there was a high probability that earthquakes could be triggered by large volumes of CO2, and we expressed concern about, the seals. My thinking has changed, and I would change one thing about this paper if I were to rewrite it now. But I do want to point out that we've made a lot of progress. We can explain the occurrence of seismicity induced by produced water injection using relatively straightforward models. We usually do this in hindsight, right? But once we know something occurred, and we look at the fault, we look at the pressure change, we look at the state of stress, and hey, it all makes perfect sense in hindsight. Because we can do that, we can avoid injection near potentially active faults when we know they are there. We can even, we did this in Oklahoma, we can predict how seismicity rate is related to injection rate. But of course, that's after it occurs and once the system is all acting. And this progress that we've made, which I think is important and noteworthy, may not be all that helpful in the case of CO2 sequestration. And the reason is this binary risk. One day you have a project and the next day you don't. And when you actually look, this is some of the work that Raul Walsh and I published originally in 2015. I don't want to take the time to explain it. All I'll say is that the rates at which saltwater were being disposed of into the Arbuckle Formation are really quite comparable to what's talked about, for CO2 sequestration in some of these basal aquifers. And there were 131 wells in this Cherokee area. That's the blue crosses, and the earthquakes are the red dots. 270 wells. These areas, by the way, are 50 by 100 kilometers. So they're really large areas, hundreds of wells, small pressure change, and yet we're still getting all of these basement earthquakes occurring using volumes, that are really pretty modest compared to, what, two of those pipelines were going to deliver 27 million tons a year to Decatur, because Decatur looks okay with a few 100,000 tons of CO2. So what I would change if I wrote this paper today is really maybe not the threat to the seal of the CO2, but it's with respect to public acceptance of the process. And we've seen this play out in many different parts of the world, in Groningen in the Netherlands, and the Midlands of the UK. if the public associates CO2 storage with induced seismicity, it may not be possible to carry out, a sufficient number of projects to really realize the benefit of having a negative carbon strategy and storing CO2 in the subsurface.
Mark, quick time check. We're at 12:51.
Okay, I've got just really one more slide after this snarky comment that it ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. And I'm not saying it's DOE that doesn't know it. I am saying it's these pipeline developers who are just, looking to, have a business doing what appears to be a public good, but it could really backfire on everyone. The Gulf of Mexico is an attractive place to put CO2 for a number of reasons. There's a lot of sources. The sands there are weakly cemented, not likely to produce earthquakes. They're also, well characterized by the oil and gas exploration. They're thick shales. All of it is quite good. And so that's where I expect a lot of action in the future. And the one place that, this is very, I think, serious concern I have about induced seismicity is probably somewhat obviated. And so it's good to see a lot of action there in the near future. And with that, I'll thank you, and I'm happy to answer questions.
Great. Thank you so much, Mark. If anyone has a question, I'd like to request that you use the raise hand feature, and then we will call on people. There we go. Arthur Lee. Arthur?
Oh, yeah. I'm trying to. Okay. Okay. You can hear me? Okay.
Yes, we can hear you.
Okay, good. No camera. Sounds like look like Cerise has turned off all of her cameras. I just wanted to ask you, Mark. First of all, hello to you.
Hello.
I just wanted to ask you when you are talking about these depleted reservoirs in terms of pressure depletion, are you suggesting that perhaps in many of these cases where we're in a well-produced region, that they could also serve then as good storage sites, good storage basin as well for CO2? Is that a suggestion that you are making explicitly or even implicitly? I guess I just want to be sure.
Yeah, well, pressure is the problem, and if the pressure has been, significantly changed by prior production, that's good, and so that would make it would certainly obviate the concern about earthquakes, and as I mentioned, there are other things you'd want to look at, but I guess I think the short answer to your question is yes.
Adam?
Hey, Mark. Thanks for the talk.
Sure.
Quick question. When we're preparing these Class 6 permits, we often use the Stanford tool for fault slip profiles. Do you have a suggestion to do something different, or do you like that technique?
Well, I was my graduate student Raul Walsh and I developed the tool, and then with actually in the end we actually combined forces with Exxon, and we released the tool to the public together. No, that's a perfectly adequate tool. It's a screening tool. It's the first thing you do to see if a fault is potentially problematic. If you're really serious about doing something at scale, you want to transition to a more complete, well characterized formation and use a detailed poroelastic simulator. But no, that's the tool. What I meant when I said the progress may not be helpful is you have to know the fault is there. And when we talk about these basement faults, we don't know they're there until they sort of light up seismically. And that's the real problem. When you're talking about injection into the sedimentary section, the faults you're mapping seismically are probably adequate and use FSP. So that's as a first step to use. So I do like that tool.
Great. All right, Don.
Good afternoon, and thank you for a fascinating presentation. Do you believe the existing regulatory framework is sufficient to help arrive at the right answer for evaluating these various locations? I mean, you've indicated some of the factors that make some good candidates and others not good candidates. Or might there be improvements to make the pathway to sequestration quicker?
Well, I know one thing that's traditionally left out is this concern about induced seismicity. Of course, everybody's aware of it now, but for example, when you look at regulations that are based on the pressure change not to exceed in the context of the frac gradient of the overlying formations. Well, of course, you don't want the pressure to get so large that, you know, a hydrofrac propagates up vertically out of the injection zone. But the really scary thing, you know, from our studies in Oklahoma and now what the University of Texas is finding in West Texas is some of these pressure changes are really small. I mean, in our case, it was probably 100 PSI in the case of Oklahoma. There are some of the cases that the University of Texas has studied, you're talking about tens of PSI, really small changes of pressure are triggering earthquakes like in the Delaware Mountain Group there. So, you know, that's really the concern, and the regulations don't speak to that at all. And what the regulations tend to do is they tend to be retroactive, okay? You know, how, you know, if you have a problem, then you do that, you know, like a traffic light system. And so we've been talking to groups like the Railroad Commission in Texas for a number of years, trying to, you know, make them aware of these concerns, especially about deep injection. All I can say is, you know, their regulatory process is a political process, and they're taking into account a lot of considerations. But I worry. I think the regulations concerning hydraulic fracturing have been much better because those are, you know, those are very interactive. You know, you're hydraulically fracturing a well, an earthquake occurs exceeding a certain threshold, you stop, right? And depending on, you know, the green light, yellow light, red light, you know, system that's been developed, and so you can react to something quickly. But in some of these other cases, it's more subtle. It plays out over longer periods of time, and you might be you know, triggering slip-on faults that you don't know about, and you know, exactly what you know, how you respond is more complicated. So I think the regulatory system needs to take all that into account, and I'm really not fully aware of, you know, what every state is doing, where the federal regulations are right now, but I think this is something that can't be overlooked, shouldn't be overlooked.
Thank you.
Great. Okay, well, thank you very much, Mark, for this excellent presentation. Thank you all for attending.